In this section, we will discuss the concept of renal clearance. Clearance is a general concept that describes the rate at which substances are removed, or cleared, from plasma. Thus, whole body clearance means the total rate of removal of substances by all organs. Hepatic clearance means the rate of removal by the liver, and renal clearance means the rate of removal by the kidneys. The concept of renal clearance is being introduced at this point because it is employed in several basic concepts of renal physiology discussed throughout the chapter. For reference, see the tables of commonly used abbreviations, Table 6-3 on page 245 of the text, and commonly used equations on Table 6-4 on page 246 of the text. In clinical practice, renal clearance is the only clearance routinely measured and applied to clinical scenarios. Table 6-4 outlines commonly used equations in renal physiology. By definition, renal clearance is the volume of plasma completely cleared of a substance by the kidneys per unit time. The higher the renal clearance, the more plasma that is cleared of that substance. Substances with the highest renal clearances may be completely removed on a single pass of blood through the kidneys. Substances with the lowest renal clearances are not removed at all. The equation for renal clearance is as follows, where C is clearance measured in milliliters of plasma per minute, U refers to the urine concentration of a substance X given in milligrams per milliliter, V is the urine flow rate per minute in milliliters per minute, and P is the plasma concentration of that same substance in milligrams per milliliter. This equation applies for all substances discussed. Thus, renal clearance is the ratio of urinary excretion to plasma concentration. For a given plasma concentration, renal clearance of a substance increases as the urinary excretion also increases. Again, the units of clearance are volume per unit time. Conventionally, this is referred to in milliliters per minute. However, this could be liters per hour or liters per day. This means the volume of plasma cleared of the substance per unit time. Renal clearance can be calculated for any substance. Depending on the characteristics of the substance and its renal handling, renal clearance can vary from 0 to greater than 600 milliliters per minute. For example, renal clearance of albumin is approximately 0 because normally albumin is not filtered across the glomerular capillaries. The renal clearance of glucose is also 0, although for a different reason. Glucose is filtered and then completely reabsorbed back into the bloodstream. Other substances such as sodium, urea, phosphate, and chloride have clearances that are higher than 0 because they are filtered and partially reabsorbed. Inulin, a fructose polymer, is a special case, and we'll discuss in more detail in the following slides. Inulin is freely filtered across the glomerular capillaries, but it is neither reabsorbed nor secreted. Therefore, its clearance measures the glomerular filtration rate. Organic acids, such as para-aminohippuric acid, or PAH, have the highest clearances of all substances because they are both filtered as well as actively secreted into the tubular lumen. Inulin has unique properties and is accordingly the only substance whose clearance is exactly equal to the glomerular filtration rate, or GFR. Inulin is freely filtered across the glomerular capillaries, but once filtered, it is neither reabsorbed nor secreted. Thus, the amount of inulin filtered will be exactly equal to the amount of inulin excreted. For these reasons, inulin is a reference substance called a glomerular marker. The clearance of any substance X can be compared with the clearance of inulin and is expressed as the clearance ratio. Thus, the clearance ratio is equal to the clearance of a substance X divided by the clearance of inulin. This equation is given again on page 246. If the clearance of substance X is divided by the clearance of inulin is 1, the substance also must be a glomerular marker, filtered but neither reabsorbed nor secreted. The meanings of various values of the clearance ratio are as follows. If the clearance of a substance divided by the clearance of inulin is less than 1, then the clearance of that substance is lower than the clearance of inulin. Either the substance is not filtered, or it is filtered and subsequently reabsorbed. For example, albumin is filtered and the clearance of albumin is less than the clearance of inulin. This is because albumin is not filtered, nothing to do with its reabsorption. In contrast, the clearances of sodium, chloride, bicarbonate, phosphate, urea, glucose, and amino acids are also less than the clearance of inulin because these substances are freely filtered, however then they are reabsorbed. If the clearance of a substance X is higher than the clearance of inulin, then the clearance ratio will be greater than 1. This substance is filtered and secreted. Examples of substances whose clearances are higher than that of inulin are organic acids and bases, and under some certain conditions, potassium. Let's walk through a sample problem as outlined on page 247. In a 24-hour period, 1.44 liters of urine is collected from a man receiving an infusion of inulin. In his urine, the inulin is 150 milligrams per milliliter, and the sodium is 200 milliequivalents per liter. In his plasma, the inulin concentration is 1 milligram per milliliter, and the sodium concentration is 140 milliequivalents per liter. What is the clearance ratio for sodium, and what is the significance of its value? The clearance ratio for sodium is the clearance of sodium relative to the clearance of inulin. Remember, the clearance equation for any substance is the urine concentration of the substance times the urine flow rate divided by the plasma concentration of the substance. All the values needed are provided in the description, although urine flow rate must be calculated. The calculated clearance ratio for sodium of 1% provides a great deal of information about the renal handling of sodium. Since sodium is freely filtered across glomerular capillaries, it also must be extensively reabsorbed by the renal tubule, making its clearance much less than the clearance of inulin. The numbers are walked through on page 247. We're given the urine volume of 1.44 liters over 24 hours. In milliliters per minute, this turns out to be 1.0 milliliters per minute. The clearance of sodium can thus be calculated. The urine sodium concentration is 200 milliequivalents per liter. The urine flow rate is 1 milliliter per minute, and the plasma concentration is 140 milliequivalents per liter. Thus, the clearance of sodium is 1.43 milliliters per minute. This is in contrast to the clearance of inulin, calculated in the same way. The clearance of inulin is determined to be 150 milliliters per minute. Thus, the clearance ratio is 0.01 or 1%. The clearance ratio of 0.01 means that only 1% of the filtered sodium is excreted. Stated differently, 99% of the filtered sodium must have been reabsorbed. This is approximately the number seen in normal states. This concludes this section. This concludes this section. This concludes this section. This concludes